In this lesson, we're going to learn about special relativity. Special relativity is a thing Einstein came up with way back in 1905. Einstein won the Nobel Prize in 1921. So this year is actually the 100th anniversary of him winning the Nobel Prize, which is kind of cool. Way back when, so the late 1800s, early 1900s, there was a whole lot going on in the world. Electricity and magnetism were kind of being figured out. A guy named Edison perfected the light bulb, so we started to have electric lights in houses and cities. And to go with that, people were figuring out how to generate electricity. So the first power plants at Niagara Falls were being built. And this guy, James Clerk Maxwell, he did theoretical work that showed the connection between electricity and magnetism. That kind of was the theory behind what these hands-on people were doing with their generators and motors and things. Maxwell's equations are what spurred, what created the whole wireless communication boom. We wouldn't have any wireless stuff if we didn't understand Maxwell's equations. In different instances, there's a few of them, but in different instances, this new physics, these new equations, particularly Maxwell's, didn't work with the old or classical physics. What we're going to talk about today with special relativity is an instance where literally relative motion, when considering relative motion and electricity and magnetism, we were getting people were seeing ridiculous situations, and so therefore that motivated Einstein to fix these problems where we were seeing these issues. Einstein's original paper that he put out in 1905 on special relativity wasn't actually called special relativity. It was called On the Electrodynamics of Moving Bodies. I've got a little simplified version of it, but basically the rest of this little video is why Einstein came up with special relativity. Not actually what special relativity is, just the why, and it shouldn't surprise us, but relative motion is part of the why we need special relativity. So we got to use our imagination. Let's say we've got two people hanging out near a wire. We'll say Alice is at rest on a neutral particle. Here's Alice. And Bob is on a positive particle. And as far as Alice is concerned, Alice sees him as moving to the right at some speed v. Also, there's a current in the wire. From Alice's perspective, the positive flow current is to the right, and the positives are moving at the same speed v that Bob is moving at. So that's our setup. Alice standing still on a neutral. Bob is moving to the right at some speed v. Below them is a wire, and in the wire the positive charges are also moving to the right at some speed v. The wire, okay, we talked about this. Maybe it came up in our Unit 3 electricity magnetism stuff, but a wire with current isn't actually charged. It's still a neutral. If you look at that diagram above, there's as many positives in the wire as there are negatives. It just so happens that some of them are moving. In this discussion, we're pretending that the positives are moving to the right, but overall the wire is definitely neutral. What we talked about in our field theory unit, because there is a current in the wire, that's going to produce a magnetic field. Since it's a positive flow, we need to use our right hand, hitchhike your hand, point your right thumb to the right, and if we can focus on where Alice and Bob are, the field would be out of the page or draw it as dots. So we got Alice and Bob above a wire. Because there's a current in the wire, there's a magnetic field where they are. The magnetic field happens to be dots. Let's think about what Alice sees. She's on a neutral particle. The wire is neutral, so there's not going to be any force on her. She's just going to sit there, no force on her. But from her perspective, Bob on the positive particle is moving to the right. So we've got a positive particle moving through a magnetic field. That is classic motor principle stuff, the QVB sine angle equation if we needed it. The right hand rule to figure out the direction of force, I do the high five hand. We've got a positive moving to the right, so take your right hand, point your right thumb to the right. That happens to be in a magnetic field that's out of the page, so point your fingers out of the page. When you do that, you should get that your palm is downward. So from Alice's perspective, there's no force on her, but there's a force on Bob that is downward. All right, special relativity is all about relative motion, all about frames of reference, so we're going to flip things. What if we flip and consider things from Bob's perspective? So this is first day of grade, well, when I taught it, the first day of grade 11, we talked about relative motion. If we think of things from Bob's perspective, he could argue that he's not moving, but Alice is moving to the left. And from his perspective, if he looks down at the wire, there's no the positives aren't moving since he's moving at the same speed as them. He doesn't see them as moving, but he would see the negatives as moving to the left. When Bob looks at Alice, Alice is on a neutral particle, happens to be moving, but she's on a neutral particle. Even if there is a magnetic field there, she's on a neutral particle. There's no force on neutral particles, so no force on Alice. That's okay, because that's what Alice thought as well. But when Bob looks at himself, he sees himself at rest. He's at rest in a magnetic field, but that QVB, that motor principle, required motion. He's on a charged particle, but the charged particle isn't moving as far as he's concerned. So from his perspective, since he sees himself as stationary, he doesn't see himself as having a force on his positive particle. So he sees Alice with no force, but he also sees himself with no force. That's the problem. Relative motion shouldn't lead to completely different outcomes. From Alice's perspective, she saw a force on Bob. From Bob's perspective, he didn't see a force on himself. That's the problem. We can't have one situation leading to two different outcomes. That's what was bugging Einstein. There must be something wrong with how we think about relative motion. There must be something wrong with how we think about time and space, because we shouldn't be getting two different outcomes. So with this riddle in his mind, Einstein literally invented something called special relativity. Basically, he rethought how we perceive time and space. I'm going to pause this video and we'll start actually what special relativity is next. It's going to seem weird and it may seem counterintuitive and science fiction-y, but it's been confirmed by experiments over and over and over and over. So as far as the theory goes, we're going with this theory as being correct. That's where I'll pause this one and I'll get into the what actually special relativity is.